Hey everybody, welcome back to FP 101X, Functional Programming. And what we're going to do today is taking the first baby steps in learning Haskell. Now, one of my favorite movies of all time is The Karate Kid. And if you haven't seen this movie, stop this, watching this lecture and go watch this movie first. Every time I need to learn something new, I rewatch The Karate Kid. And I can tell you, I've seen it, maybe 20, 30 times. And every time I watch it, I learn something new. If you watch the movie, you will see that the boy here, Daniel, wants to learn karate. And Mr. Miyaga, that's the gentleman here on the other side, makes him do a lot of what Daniel thinks are pointless exercises. And he gets kind of frustrated. But in order to learn something, you have to go through a lot of exercises because there's a lot of muscle memory, or in case of programming, you have to have the muscle memory in your fingers. There are certain things that you should not have to think about, that you have to drill, that you have to do over and over and over again. And that's what we are going to do in this lecture today. So don't get frustrated, don't be like Daniel, be a grown-up, and just do your exercises on and on. Wax on, wax off, wax on, wax off, until it becomes completely automatic, and then you can use your brain to solve the real problem. You don't have to think about the basics anymore, okay? And every time you learn something new, rewatch this great movie. All right, let's show some Haskell. The Haskell implementation that we're using in this course is the Glasgow Haskell compiler, sometimes also called the Glorious Haskell compiler. And GHC is the leading implementation of Haskell. And it has both a compiler and an interactive REPL loop that you can use to type in your code. And the interactive nature of the GHC interpreter makes it really easy to experiment with Haskell, and that's why it's also very useful for this course. Many of the exercises that you will get during the course, you can do by using GHC. I don't care, I don't see that as cheating, because as programmers, we should really use the compiler to help us, okay? So the computer is there to help us program the computer. If we don't use that, that would be stupid. So GHC is freely available from that website here. That will also be on the course website. So, and you can also Google or Bing for the Haskell platform, and it's available for all major platforms, Mac, Windows, and Linux. To start GHC, you just type from the command line GHCI, and then you get some text blurbs, and there you see a prompt, prelude, and that's where you can start typing in expressions. For example, we can type in an expression 2 plus 3 times 4, and the result of that, the GHCI, will then print the result for that. So in this case, we're really using a GHCI as kind of a calculator. It's a little bit like a calculator on a command line interface instead of a calculator with buttons. What we also see here is that since 2 plus 3 times 4 apparently is 14, that multiplication binds stronger than addition. And so there's no surprises there. Most languages have that. And if we want to first do the addition and then the multiplication, we have to put parentheses. So we write 2 plus 3 times 4, and then the result is 20. And we can do more complicated expressions like the square root of the 3 to the power of 2 plus 4 to the power of 2, and we get 5. As you saw, there was this kind of the prelude prompt here. So in the Haskell prelude, it's like the SDK for Haskell. These are all the standard functions that come for free with Haskell. On the website, we will tell you how to get other libraries for Haskell, but we won't discuss that in too much detail right here. You can read up on that. We'll try to stick with just the standard library functions, the standard prelude. And a lot of the functions in the prelude are functions over lists. And we're going to kind of walk through a couple of them, and then in later lectures we will implement these functions in several different manners. So the first function here is head, which takes a list, and the way we write lists in Haskell is with square brackets and the elements separated by commas. So the head of 1, 2, 3, 4, 5 is, unsurprisingly, 1. The tail, that's the opposite of head, so it is everything on the list except the head. So the tail of 1, 2, 3, 4, 5 is the list 2, 3, 4, 5. We can also select the end element of the list with this double exclamation mark operator. So if we want to select the second element of the list, 1, 2, 3, 4, 5, we get 3. So what do we learn from this? Well, that the first element of the list has index 0. Okay, so like it should be, Haskell starts indexing lists by 0. Now there's 2 exclamation marks here, and there's a good reason for that. Because in Haskell, lists are not arrays. So indexing into the list here at the second element will traverse the list. So it will traverse the list, throw away 1, throw away 2, and then return 3. So this is not a constant time operation. So indexing into a list, unlike indexing into an array in Haskell, is linear in the length of the list. So, or linear in this number, but in general linear in the size of the list. But fortunately, we will hardly see uses of this operator in practice. And if you find yourself wanting to use list indexing, then you know that you have not done enough wax on, wax off, wax on, wax off. You're still too much in the mindset of imperative programming using arrays. And in Haskell, we typically use higher order functions like map, filter, fold, and not indexing to perform complex operations over lists. Here's another example, take 3. It takes the first 3 elements of a list. So if we have the list 1, 2, 3, 4, 5, guess what? It returns the first 3 elements, 1, 2, 3. Drop is the opposite, so it takes a number and a list, and it drops the first 3 elements of the list. So in some sense, drop and take are the generalizations of head and tail. Head and tail just take the first and the rest of the list, and then with take and drop, you can generalize that to arbitrary numbers. Calculating the length of the list, all right, we do that by saying length, calling the function length. Length of 1, 2, 3, 4, 5 is 5. And again, lists in Haskell are not like arrays in other languages. So taking the length is not a constant time operation. It takes its time linear in the length of the list. Sum sums up all the elements. So if we call sum of 1, 2, 3, 4, 5, the result is 15. Product is the same as sum, except instead of adding up the numbers, it multiplies all of them. So multiplying 1, 2, 3, 4, and 5. It's like taking the factorial of 5 is 120. Appending 2 lists is another common operation. You take 2 lists and you smash them together into a new list. So if I append 1, 2, 3 with 4 and 5, we get the list 1, 2, 3, 4, 5. And then the last function here on this slide is reversing a list. Reverse 1, 2, 3, 4, 5 gives you 5, 4, 3, 2, 1. In the rest of these lectures, we will define all these functions ourselves in several ways. But right now, it's good to kind of play with them to see what they do, and then we will be ready to implement them. Then we will know what they're supposed to do. Here's another very important slide. And that is about a function application, because Haskell is very different than mathematics on the one side, and very different from other programming languages as well. In mathematics, when you apply a function, mathematics that you do in school or college when you take analysis, when you apply a function to an argument, you always use parentheses. So in this case, when we apply the function here, this is applying the function f to the arguments a and b, and then adding c space d. Now, in mathematics, typically, and that comes from physics, is that space means multiplication. All right, so if you look at a mathematical textbook and you see, c space d, it usually means c multiplied by d, and therefore, when you apply a function, you're using parentheses like this to disambiguate. Since in Haskell, function application is used much more often than multiplication, whereas in physics, multiplication is used more often, so that's where multiplication is given the kind of, the most white symbol, the least kind of visible symbol, the most white spacey symbol. In Haskell, function application is denoted by white space, so that it's not so much in your face. So in Haskell, instead of writing f of a comma b plus c space d, function application becomes denoted by a space. So it's f applied to a, applied to b, plus c times d. All right? And most programming languages, you would write f paren a comma b close paren. So they are in some sense the worst of two worlds. There, you have to write everything explicit. But in Haskell, we make the decision that function application is done by using a space, and multiplication is done by using multiplication. Also, function application binds stronger than any other operator. So if you see f of a plus b, that means f applied to a plus b. So it doesn't mean f applied to a plus b. Okay, and this can get, people have to get used to this. So this doesn't mean f times a plus b. It means f applied to a plus b. So that's kind of similar to multiplication binding stronger than addition. Okay, here's a table that gives you some of the, a couple of more expressions. On the one side, Haskell, and on the other side, mathematics. So this is what you should forget. So I'm going to stand in front of that. This is what you should forget, and this is what you should learn. All right? So forget what's behind me, and learn what's on this side. Okay? So instead of f, open paren x, we write f space x. Instead of passing two parameters to f, we apply f to x, and then apply that result to y. Instead of f, open paren g, open paren x, we can write f of g of x. And later we will see that we can write that using function composition, f as f compose g. Okay, and there the rest of the examples should be obvious. Okay, but if you just look at the shapes of these two, don't try to interpret them, you will see that the Haskell code here looks much lighter weight than the code on this side. Okay, and Haskell programmers are lazy, we don't want to type too much, so this looks much more beautiful than this, and that's why Haskell syntax is designed the way it is. So thank you. This was the end of part 1. See you in a bit for the remainder of chapter 1.